So welcome everyone to this presentation on multi-sensing nanoware with electrical contact resistance and friction measurement. The work is a collaboration between ourselves at Micromaterials Limited and also Manchester Metropolitan University and the University of Leeds, all in the UK. So I'll begin my presentation by talking about single asperity tribology. Then I will move on to introducing our new capability for reciprocating nanoware, which we've called the nano tribo test. I'll present some results in diamond-like carbon coatings on the biomedical alloys 316 stainless steel and titanium 64, and on thin multi-layer films, and also on bulk silver and gold alloys. And in the latter measurements, we've integrated electrical contact resistance measurement to understand more about the failure mechanisms. So if we think about a conventional tribological test, the real area of contact is a small fraction of the apparent area of contact, and the contact zone is hidden, and this makes it difficult to really understand the pressures driving the failure events that we see. What we can do is we can simplify these contact conditions by moving to a single asperity contact and control these conditions and apply an applied load, and therefore we've got a really good idea about the height with these locally high pressures about what's driving the failure events that we see. So we've been involved in single asperity contacts for some time because these are possible in our nano-test Vantage system, which is a nanomechanical and nano tribological test platform. And we've added a new module into this, which we've called the nano tribo test, which allows us to do these rapid high cycle linear reciprocating nanoscale wear tests, either with very short wear tracks or right up to 40 millimeters. And these tests can be combined with electrical contact resistance measurements when we use conductive probes. And therefore we can study the electrical endurance of sliding metallic connector materials. So if we look at the typical conditions in the various nanotribology modules in the nano-test Vantage, we can see that this new module dramatically extends the speed and sliding distance range. This ability to perform tests at much higher sliding speed while retaining this nanoscale precision is particularly useful for direct simulation of MEMS devices, also for looking at microtribology of biomaterials, the electrical endurance of sliding electrical connector materials, and also reciprocating contacts in hard coatings. So this is an example of the latter. It's a multi-layer diamond-like carbon coating deposited on hardened M2 tool steel. And this is a snapshot near the start of a 500 cycle test at 500 millinewtons sliding against a 25 micron end radius diamond probe. And what we can see is over a relatively small number of cycles, the friction starts to increase, and we've got the sensitivity to follow the wear evolution cycle by cycle. If we convert the raw friction trace into friction loops and then take the average friction over a friction loop, when we can easily plot friction coefficient against number of cycles. And we can see here that we can pick up quite nicely this increase in friction occurring near the beginning of the test in these two tests here. If we look at the other test, we can see actually something slightly different is happening. It's much more jagged frictional response. So we looked in more detail with SEM, and we can see here that in there's a sort of partial failure, fracture of the scratch track. So in some regions, like in the center here, it's just a normal wear track, but here you're getting a transition to a more fractured zone. So if we do EDX, we can see there's a lot more tungsten in this, a little bit of chromium, and maybe a little bit of iron. So this is a fracture within the coating system. So this is all very useful information for coating designers. So if we move on now to the biomaterials, so stainless steel has a very sort of ductile response when you look at these SEM images of its wear tracks and very low friction. But in contrast, the titanium alloy, similarly ductile at low load, but there's an abrupt transition at high load. So you can see here on the left in this example at 50 millinewtons, it's relatively low friction, and then suddenly after about 15 or so cycles, then you're going to abrupt change to a high friction regime really within a small number of cycles. You can also see this clearly in a high load test on the right. So cumulative energy dissipation can also be used to follow this, and you can see quite clearly this transition as a function of load here and cycles. And we just to mention that when we look at the friction coefficient, we're actually recording the dynamic friction coefficient. So this is the friction coefficient under full sliding. So what is behind this? Well, at 40 millinewtons, the passive oxide that protects the underlying titanium alloys is not worn away by the 500 cycles in the test, and there's no oxygen enhancement in the wear track. However, starting at 50 millinewtons, then you get this abrupt transition to this much more fractured surface, which becomes progressively greater at higher loads. So this tribologically transformed structure breaks up the initial oxide, and you create this much more heavily deformed area where there's a lot of tribal oxidation occurring as well. And this explains the frictional increase. So we'll move on now to the electrical measurements. So we start off looking initially at a multi-layer thin film stack with a top layer of 50 nanometers of gold, and then there's silver and nickel underneath, and it's on a copper alloy substrate. And we're sliding that against a 1 millimeter steel ball at 10 millinewtons. And we're interested to try and understand which is more sensitive to failure, the friction or the electrical contact resistance, what is the extent of correlation between these two, and how does the failure evolve over the whole track. So if we take a typical test, and these are just 4 snapshots at different sliding distances. The first one is starting at 280 millimeters of sliding, because nothing happens before that point. And we can see the friction stays low, the electrical contact resistance stays low right up until we get these small isolated events occurring just after 340 millimeters sliding. If we run that test on, we can see again these periodic small events. Run it on a bit more again, we can see these relatively small isolated failure events. And we run the test on a lot further, and we can see progressively more of the test sample is failing. So how do we understand that? Well, we can look at the raw electrical contact resistance signal as a function of time, in this case converted to cycles. We can see these occasional spikes, but then it's a rather complicated picture. You could look at spike density or something like that. But one thing that we thought might be interesting to look at was to compare the mean electrical contact resistance per cycle and the friction per cycle. And when we do that, we can see there's quite a clear correlation, at least in these tests. It's a little bit more complicated in the tests on bulk noble metals. So with bulk noble metals, these are much more resistant to sliding failure. And this is a test at much higher load now on a bulk silver alloy sliding against a bulk silver disc. And we can see here this instrumentation has the stability for 35,000 cycle test. And in this particular test, you can see a couple of spikes in the friction and the contact resistance. And in these spikes, the oxide debris potentially, we speculate, is getting trapped in the contact, and it's gradually working its way out of the contact. But this is a slow process, and it maybe takes a sort of 1,000 cycles to complete. But at the end, we're back to a low electrical contact resistance. So hopefully I've given you a flavor of some of the potential of this nano tribo test system, which we developed for rapid high cycle linear reciprocating wear testing. So we've enabled it to have automatic recording of the friction loops and the cumulative energy dissipation, and combining those with electrical contact resistance. And this multi-sensing approach is particularly useful to improve our understanding of the onset of wear and the subsequent evolution of the failure behavior. So the instrumentation design retains the high lateral rigidity in the load head, which provides the stability to perform these tests for several hours. And we've gone right up to, as I say, 35,000 cycles, and even 300 millimeters of sliding distance, which is an extremely large sliding distance for a nanoscale test. So if you're interested in further information, please check out the paper shown here, or contact me by email, or check out the website shown there. So thank you very much for your attention.